Hello, so this is video number 3 of section 5.2. This video, we're going to work through the following problem. We're sort of going to bring everything we've learned so far together. Well, a little bit, mostly everything. Everything concerning eigenvalues and eigenvectors, I guess. Well, we've learned some other definitions, but basically what I wanted to do is start from scratch with a 3x3 matrix, work through the process of finding all of the eigenvalues, all of the eigenvectors. This is something that is useful to know how to do and that we might do at one point or another throughout the course. So on homework or on a test or something like that. And so I wanted to just go ahead and work through it. So it's a little bit of a lengthy process. And so we'll sort of go through all the steps. Towards the end, there's some row reducing that I think I will probably leave out in the video. But certainly if you have questions on the row reducing, I'm happy to answer those. So also, given what we've built up thus far, this problem is very doable with the material and the knowledge we already have. So like always with a lot of these examples, I highly encourage you to pause the video here and try to work this out on your own, and then watch the solution. So without further ado, let's get started. So first thing, before we can find the eigenvectors, we need the eigenvalues. So if we don't know the eigenvalues, this is always our first step. So remember, we want all roots of the equation determinant of a minus lambda I. For here, this is a polynomial in terms of lambda, which is a variable. And so, of course, we want to write this out maybe in matrix notation. And again, all this is calculating the determinant of the matrix, where I just subtract lambda from each diagonal entry of A. Like that. So there isn't, well, I guess there is one preferred column to expand across here. And so I'm going to expand across column 3 because there's a 0. I suppose you could also use row 2. And certainly you could use either one of the other 2 columns or rows if you wanted to, but remember, zeros make this easier because every time we expand across a row or a column with a 0, we sort of lose, I guess in a sense, lose that term, or just one less term to work with, so it's just easier. And so, of course, because the 0 sort of eliminates one of the terms, we can rewrite this as as a combination of 2 smaller determinants. And then I'm going to now calculate each of these. And so if you do this, this is the determinant of -2, or the determinant of this is equal to -4 plus lambda minus 12. And so this is equal to -2 times 6 lambda, -2 times 8, 9. I shouldn't do too much in my head. -2 times 9 minus 2 lambda. I'll just work it out here. Do one more step. So this is -3 minus 3 times 4 minus lambda minus -3, which is plus 3, right? So this would be plus 3 minus lambda times -1 minus lambda times 4 minus lambda plus 12. And so expanding these and simplifying. So inside here, notice we get 12 minus 3, which is 9, minus 3 lambda. Distributing the 2, this term becomes 6 lambda minus 18. We're distributing -2. Working out the inside of this equation, we get 3 minus lambda times. So after sort of working all of this out, you get lambda squared minus 3 lambda plus 8. So I wanted to briefly go over sort of this step because notice here in this polynomial, if we were to multiply this out and sort of expand everything, we would end up with a cubic polynomial. And cubic polynomials are somewhat difficult to factor. Right? We have a fairly good way of factoring quadratic polynomials. So certainly, if the degree is 2, I can either sort of use some factoring tricks to figure out the roots, or I can use the quadratic formula if all else fails. Cubics are a little harder. So sometimes it takes a little bit of guessing, right? The right first root, and then you can do some polynomial division. But so whenever we're given a problem like this, we always want to be kind of thinking as we go, looking for tricks. And one specific trick you want to look for whenever you're given a problem like this, especially in the class, right? Because usually, usually these problems will have sort of little tricks that make them easier to solve. You want to look for a way to factor this before it becomes a cubic polynomial. And so the way that we can do this here is by noticing that before I multiply 3 minus lambda here, I can actually factor out a 3 minus lambda from each of these terms. So if you'll notice, this is equal to 3 minus lambda times negative 6 plus lambda squared minus 3 lambda plus 8. And so all I did was I factored out a 3 minus lambda from each of these terms. This term was left with a negative 6. This term was left with lambda squared minus 3 lambda plus 8. And so notice before I ever get to the point where I have to factor a cubic polynomial, I'm left with a slightly easier polynomial to factor because it's degree 2. So always look for a trick like this, sort of this step here. This is another reason why I wanted to go over this, because oftentimes with these cubics, not always, sometimes you'll have to kind of do a little bit of work to figure out how to factor these, but oftentimes if you're given a problem like this, look for factoring tricks like this. So anyways, all of the eigenvalues of A are the zeros of this equation. So we know that A has 3 eigenvalues, which I'll list up here. We'll do it in blue. Lambda 1 is equal to 1, lambda 2 is equal to 2, and lambda 3 is equal to 3, are the 3 eigenvalues of A. So now we want to find the eigenvectors. And so certainly each eigenvalue should have one eigenvector corresponding to it, at least one. Oh, I did not want to erase A. Sorry for that. I'll rewrite A on the board here. A is equal to negative 1, negative 3, negative 3, 4, 4, 1, negative 2, 0, 3. So, and unfortunately, we kind of have to work through each eigenvalue separately. So this is where I said like the process can sometimes be a little lengthy. But so remember, so we'll start with lambda 1 equals 1. Any eigenvalue or eigenvector for lambda 1 must be a solution to, well, A minus lambda 1 times I times x is equal to 0. So all we want to do is row reduce now the matrix where I subtract 1 from each diagonal entry of A. So notice that this matrix is the matrix A minus lambda 1, which is just equal to 1 times I. So in general, if you don't want to write out each of these steps all the time, you can remember, just take the matrix where you subtracted the eigenvalue off of all the diagonal entries. So another nice sort of way to sort of check this process as you're going is that if this matrix is an eigenvalue, and so I'll do a couple steps here at once. I'll do -1/2 row 1 and 1/3 row 2 to get some leading ones where I want them. So that should be 1, 0, -3, 1, 2. So sort of a way to check your work as you're going is that each of these eigenvalues, right, when I subtract them off of my matrix A, the corresponding matrix should not row reduce to the identity. Because remember, we're looking for non-trivial solutions to this equation. And so we know that a non-trivial solution only happens when I can row reduce this and get at least one free variable. So if you subtract the potential eigenvalue off the diagonal and you do not get a free variable in the homogeneous equation, you know you've done something wrong. Which is always nice to sort of keep those, it's good to have those sort of checking methods available to you as you work through these problems, because, especially with eigenvalues and sort of moving on with some of these problems, the process can sometimes get very lengthy and involve a lot of work, and so it's important to know the methods that you can use to sort of self-check your work as you go. And so certainly here, because I subtracted 1 off of each of the diagonal entries and was able to row reduce the matrix to something that has a free variable x3, that means I know that 1 is in fact an eigenvalue. So what did I do? So I took my first potential eigenvalue 1, which I had calculated, row reduced to the matrix where I subtract 1 off of A. And so I want to somehow figure out, okay, what's a solution to this system? So remember, this corresponds to x1 equals the free variable x3, and x2 is equal to the free variable x3. And so notice I got each of these equations by subtracting x3 over. So if I let x3 equal 1, this means that the following is an eigenvector. Is an eigenvector. And so remember, this is the vector that would appear in the parametric vector form of the solution to this matrix, or of the homogeneous solution corresponding to this matrix, excuse me. So we'll sort of list the eigenvectors, and I'll call them v1, v2, and v3, and we'll do it in blue to differentiate them. We'll list them here off to the side as well. So we know that the first eigenvector v1, which corresponds to lambda1, is equal to 1, 1, 1. And so there's actually something interesting that I have in the worksheet, and I want to mention. If you sum, so there's the eigenvector 1, 1, 1 is always an interesting vector, because notice that basically multiplying any matrix by the vector 1, 1, 1 outputs the vector who's equal to the sum of all of the rows of A. So notice that this vector is an eigenvector of a matrix whenever the rows of that matrix all sum to the same thing. So notice if you sum across the rows of A, they all sum to 1. And so 1, 1, 1 is an eigenvector of A corresponding to 1. And so sort of more interesting things you can learn about eigenvectors, that this eigenvector, or if this is an eigenvector of the matrix, it means that the row sums of the matrix are all the same. So lambda 2, so remember this is lambda 2 is equal to 2. And so we want to row reduce. And so here I'll probably start moving a little quicker. So now we want to row reduce the matrix where I subtract 2 from each of the diagonal entries of A. And so notice here, this time I've subtracted 2 from each of the diagonal entries. And I don't want to keep all the fun for myself, so I will let you row reduce this at home. But row reducing this, I get the following matrix. Nope, not negative 3/3, negative 2/3, negative 1, 0. So after doing some mythical row reduction steps, I got from here to here. And so remember then to find, you can write this in parametric vector form. And so remember, since x3 is our free variable, it sort of corresponds to this free parameter t. And then we know that x1 will always be 2/3 times x3, and x2 will always be 1 times x3. And this vector here we get is an eigenvector. So we would know that eigenvector v2 corresponding to lambda 2 is equal to 2 would be the vector 2/3, 1, 1. All right, so one more to go. We want to now calculate the eigenvector corresponding to lambda 3 is equal to 3. And so notice all I'm going to do here now is subtract 3 off of each of the diagonal entries of the matrix. So I can change my starting matrix by just doing this. And then again, doing some mythical row reduction steps. I can row reduce this to the following matrix. 1, 0, negative, sorry, 1, 0, negative 1/4, 0, 1, negative 3/4, 0, 0, 0. And so parametric vector form, solution, well, remember x3 is my free variable, so that will correspond to the, we'll let the parameter be s, and then I know that 1/4, 3/4 should go there. And so that gives me my final eigenvector corresponding to, put it over here, lambda 3 is equal to 3, 1/4, 3/4, 1. So there you have it. Started with a matrix. We calculated its 3 eigenvalues. Doing the same process for each eigenvalue, where I subtract that off the diagonal, solve the corresponding homogeneous equation by row reducing, looking at the parametric vector form of that solution. And again, you can set this free parameter equal to 1. Alternatively, I could have set it to 4, and I would have gotten an eigenvector of 1, 3, 1. Doesn't matter. Just taking this vector, I get 3 eigenvectors, all corresponding to here lambda 1 equals 1, lambda 2 equals 2, lambda 3 equals 3. So that's how you sort of can work through finding all of the eigenvectors and eigenvalues for a 3x3 matrix. So that wraps up section 5.2. This process will come in great use in the next section where we learn how to diagonalize a matrix.